Yeah, so I'm going to start again. So today, yes, I need some, some energies on the, I'm going to put some of this again on my coffee. Yes, great. Yeah, please, I'm going to about to start the class. Yeah, so, take this. Okay, thank you. Thank you. Hey, ROS developers, welcome to a new class of the ROS Developers Live class. I'm very happy to have you all here. And today, so I'm ready, actually. I was just preparing my coffee. So let me show you that I have my coffee here because from the previous class, there was somebody that was complaining that I was not drinking coffee, some kind of alcohol or something. I don't know what they were suggesting, but as you can see, I'm drinking coffee here. So it's just coffee with a little bit of milk. That's it. So yeah, because I need it for my class. It's nice, so it gives me some energy. So let me just drink to your health. Okay, and let's start with the class. I am ready. Yes, I can feel the energy of the coffee. And then what we are going to do is, as always, as you know, this class of today, it's about using ROS plus Gazebo plus OpenAI to train a robot. Very simple robot. It's a carpool. But it's a good example to start here. So what we are going to do is, as always, let me explain for the new people that it's arriving. So you can see that we are going to use a system that is called the ROS Development Studio. So you can practice at the same time as I am explaining. So you will be following the same instructions. And that's a web-based platform that is called the RDS. Okay, so you can go to rds.theconstructscene.com and create a free account and start doing this. So what I'm going to do is to share with you the project of today that contains the instructions, the notebook, some code, simulations, etc. So I'm going to share this with you through that platform, and we are going to start, okay, to work with that project of today. For that, what I'm going to do is to capture a link from the ROS Development Studio and paste it on the chat of the Hangouts that you can see there. And that's it. You will have to click, and that's all. Remember, if you have questions during the class, don't hesitate to ask the questions on the chat also. Okay, then let's go to let me share my screen so you can see what I am doing, okay? So just a second, it's here. Share screen here, application, which one is this one? Yeah, share. And Pascal is asking the web simulators link, please. Okay, it's not a simulator, but it's a complete environment. So it's the constructsim.com. Oh, yes, the constructsim.com. So that's the web. You should have created an account previously. So if you haven't, then very bad. Very bad. You should come prepared. It's on the instructions of the video. Come on. So let's go straight. So here I have my project for today, for this class number 21 already. And what I'm going to do is to share this with all of you. So for that, it's very simple. Just share link, and then I create a share link of that project. Then I copy. And because the chat in Google, YouTube, it's very wrong, so I had to shorten, because otherwise the chat does some stupid things. So I'm shortening, copying it, and pasting now. Right now, I'm pasting it on the chat. So you listeners, the ones that are watching now the live class, just click on that link, and then this project here will appear directly in your account with all the material that is contained inside. No need to git clone, no need to share files, no need to, just a simple link, and then everything is ready. The simulations, the code, the notebook. Wow, that's so good. That's so good that I need to have another drink of my super coffee of today. So I'm waiting for some seconds, some seconds more. So everybody is clicking on the link and having the project there. Once you have it, remember, let's open the project here. Press open project and let's open. Great. So you should be there in one screen like this, more or less. Okay, then Pradeep, he says the link is working. Let's start. Pradeep is eager. Yuan Zhao, Tony, for the people that we know him, Yuan Zhao is Tony also. He says it's working. Tanya, great, very good, Tanya. Hi Gao in, okay. So people is getting into the project. Okay, Pradeep, yes, I know you are eager to start, but we have to go at a medium level of velocity because otherwise some people cannot follow. So some others go very fast and some others. So just be patient a little bit. Okay, we are going to follow everything. So let's go. First thing, let's open the notebook. For that, go to the tools and open Jupyter Notebook. So you should have this screen and then select the Live-Class 21 file. Then the following documents should open for you here. Okay, so that's the document about the Live-Class number 21. Remember that you can use this later after this class. What is this class about? Okay, so what we are going to do is to use a QLearn algorithm to train a robot to do some task. And for that, we are going to use the OpenAI GEM libraries that are provided in Python. And we are starting now to classify the level of the classes because we see that some people cannot follow. So sometimes the classes are going to be low level, sometimes higher. This is a medium class because you need to know how to create packages, set up dependencies in ROS, how to create a launch file, how to publish and subscribe to topics, and create a ROS service code, and how you can create and set up the URDF of a robot, and how to attach controllers. Okay, so remember that we are going to provide everything done already, but if you want to understand what we are doing and what we are following, that's what we suggest that you should have as a knowledge, I mean. Okay, so let's continue. Yeah, so we are going to use the ROS Development Studio. And here, if you click on this cell and press play, then you should get this screen that is the YouTube video that contains this class. So afterwards, you can press here, and then you will see the class again. If I connect now, I can see the class in real time. Okay, so not necessary because I am giving the class, so I don't need that. Okay, so what are we going to do? So what we are going to do is to make a card platform learn how to balance a pole. So you can see in this GIF here, this is an example. So we have a platform here that we are calling the card platform, and that contains a pole on the top. And then this pole is connected through a joint, and it's a free joint, so it doesn't have control. Okay, so it's a free joint. It can move. If you just push it, then it will move this joint here, and then the pole goes to one side or goes to the other. But what we want the robot is to learn how to move, as you can see on the GIF, in order to make that the pole doesn't fall down. So that's a typical example of reinforcement learning, how to teach a system to learn how to take an action in order to accomplish a task. So that's the example that we are going to do. And what do we need for that? Well, the first thing that we need, because we are talking here about robots, okay? So it's not just a simple thing like that, like a 2D something. No. We want to use the tools that we are using with ROS and with robots. And for that, we are going to use the Gazebo simulator. So we are going to have and create a Gazebo simulation of the car pole, the equivalent to this. And then we are going to apply the QLearning algorithm. And so we are going to see how it works, the QLearning algorithm. And then we are going to create an environment file. Actually, I'm going to provide that. And then I'm going to explain what is the environment file for. And then finally, what we are going to is to put everything together so we make the robot start training. So the robot will start training and try to balance the pole and start learning how to balance the pole. Okay, so that is the goal for this class. So let's go, because we have a lot of work to do, and today we have to finish a little bit earlier. So let's go. First step, to create the Gazebo simulation. Okay, so far so good. I don't see any questions there. I suppose that everybody, it's okay. There's still people arriving. Dodo, hello. Jassy, hello. Good coffee, hello. Yes. Okay, no questions. I suppose that everything is following. Great. Everybody's following, I mean. And then let's go. And let's talk about the simulation. Okay, so we are not going to create here the simulation. We show in the previous month how to create simulations for Gazebo. So please go to the other classes, live classes of the last month, and then you will see how to create those simulations. So I'm just going through it very quickly. Okay. Basically, what we are doing is to create the links of this simulation. One is the bar. The bar is the one that is here. Is this, well, actually should be called the pole. It should be the pole, yeah. And let me see here, yeah. So that is the pole here that we have here. And this is the first link of the simulation. Then afterwards, we have the base link. That is the base that we have here, is the card. Let's say the card that is here. And then finally, so we have the foot link, that is all that line on which the robot is able to move. Okay, so the robot is able to move around this bar in order to balance the pole, so not allow the pole to fall to one side to the other. So basically, we are defining those links, connecting them through joints. And let me see, where are the joints? Here, there are the joints. There is one joint between the base link and the bar. And then there is another one between the base and the foot. Of course, yes, and the line where the robot is going to move through. And then we have to include the transmissions also. We are using an F4 joint interface for that, for controlling both joints. You can use also velocity. It depends on how you want to create your simulation. It doesn't matter, actually. It depends on the command that you want to send to the controller, either a position or either a velocity. In this case, we are sending a position. Okay, so because we are using an F4 joint controller. And then, yeah, the only thing is here, we are loading the plugin of the ROS, the Gazebo ROS control. Just very quickly, okay? So about the simulation. And yeah, as something that is interesting is that we are using a Revolute joint. The Revolute joint is the one that is linking. Let me show you. The Revolute joint is here. The Revolute joint is this one, the one that is linking the card, the black part, with the bar. This is a Revolute, so it can rotate indefinitely. And then a prismatic type of joint between the card, that is we call the base, and the line of where the robot can move through. Okay, so that's it. Then what else? So here, this is the configuration file for the controllers and the PID values that we have applied. Just very, very simple. Okay, so don't worry too much. It's just taking that the work, and that's it. Remember that we are also loading the controller for the joint state controller, so the joint states are provided. Then Adam is asking, where do I find the Jupyter notebook file? For that, you have to go to Tools, and Dodo is answering. Thank you, Dodo. So you go to Tools and Jupyter Notebook. Then you will find it. You will get this screen here. Okay, so we have the simulation, but yeah, we want to launch it. Let's launch the simulation. So for that, let's open the code here in the tools. Let's go to the IDE and tools, and then you will see all the files that you have received with this project. Then let me open here, and you can see that in here you have different workspaces. Okay, so in this case we are using the notebook workspace for the notebook of the class that you can see here. So that's the notebook workspace, and then we have the simulation workspace where we have put the carpool description of the simulation. So here it is already, the simulation as it's been described here. Okay, so with some additional launch file for you, and the URDF, well, is here. Okay, so let's launch the main launch so we can see that the simulation is there. So if we go again to tools and open a shell, then open a shell, and let's put it here. Let's launch the simulation. The simulation is in the carpool description package, and let's launch the main launch. So ROS launch, carpool description main dot launch. So if you launch it like this, then the simulation, it's running there, okay, with all the controllers, etc. Oh wait, but where is the simulation? Because it doesn't show. Oh yeah, so for that we need to open the Gazebo window that is here in tools, Gazebo. There it is, the simulation. Okay, so we have that simulation here running. Great, great. And one thing that you can check is that the simulation is a stop, as you can see, by default when it starts. And if you press play, then as you will see, the physics engine is started, and then the pole is falling down. Yeah, and hi Gao is indicating, could you type ROS launch text? Yes, it's, let me write it down on the chat. So it's ROS launch again, carpool description is the name of the package and the name of the launch file that you want to launch. So it's main.launch. So you got it there on the chat. Wow, that coffee was strong. Yes. Finished the coffee. Okay, so we have the simulation here. Okay, so far so good. One step done. Second, it's about the QLearning algorithm. Second step, it's well, it's about this class. It's about teaching you how this reinforcement learning loop works. So let me go briefly about around this. So basically, this image represents what a reinforcement learning problem is. And in a reinforcement learning problem, we have an agent that could be our robot that is on the simulation. Let me open the simulation here, put it here, maybe so we can see what we are talking about. Then we have the agent that is the robot here, and that takes an action. For example, I'm moving to one side, to the left, to the right. Then this action, takes some effect on the environment. That's the whole place here that the robot is located. So if the robot moves to the right, then it means that the robot will move to that position of the environment. Then also in the environment, we are computing how good this movement, this change in the environment, how good it has been for the task that we want to solve. In this case, the task that we want to solve is to maintain the pole vertical. So that's the task that we want to solve. So this environment checks, okay, you have moved here, then the pole has fallen down, so your action was very bad. So it will give a reward, a score. It's a score that is computed on the environment based on what is the result of the action. So what is the result? then the result is that the pole has fallen down. Then the reward will be very bad. And then the state is the new situation in which the agent is. That means the robot in this position and the pole like this. So at the next step, the agent, the robot will say, oh, okay, so if I have done this movement and then my current situation is this one and the reward was so bad, then let me try that other action. So by doing this exploration, the robot can learn the proper actions to any task. Well, in theory, that's in theory. Then the learning algorithm that computes which action to take based on the state and the previous state and the previous reward, based on that, which action to take, there are many different algorithms. And one of them is called the QLearning. And basically the QLearning algorithm, it is this equation here that what it does is basically construct a matrix of values, of probabilities of ending the task correctly based on the state at which you are and the action that you have taken. So if you are in a state where the pole is just a little bit to the right, for example, and you have moved to the left, let's say to compensate, then maybe your QLearning, as it learns applying this formula, then it will learn that it's a good movement to, in that situation, to move to the left, because it's going to compensate the amount of inclination to the wrong side. Actually, it will be the opposite. If it's inclined to the left, then you have to move to the left. Exactly. So that would be the correct. Then we have some parameters that allow us to tune the learning algorithm. This is for the QLearning, and we have the learning rate, or actually this is not discount factor. This is not correct. Learning rate or alpha. This is not correct. And discount factor or gamma. Yeah. So, okay, you can correct because the learning rate is here and the discount factor is here. Okay, so this is the equation, and those are parameters that you can tune. And based on those parameters, you can finish ending learning faster or not learning at all. So it depends a lot on those parameters. And many times when you apply the reinforcement learning, you have to do a search of which ones are the correct parameters and tune many things, as you are going to see in a few minutes, that we are creating a configuration file for all the parameters that we are going to use. Okay, so those are two parameters. One, the learning rate is, well, this indicates how, so if you learn a new, you get a very good reward for one action, then how much that good reward is going to replace the previous information that you have learned at the given state that you are. So it determines basically how fast you are going to learn new information. And then the discount factor, it's about the importance of the future rewards. It means how much your future rewards are going to affect your current state. So that the best thing to understand this better is to play with those factors once you have the system running and learning. And then you can see the different effects that those values can provide. So I have included here a link that if you press, this is super nice link that describes step-by-step the QLearning algorithm in a very simple way. So I highly recommend you that you have a look at this, because it's for a simple example and you will understand that basically this is what the QLearning is building, this matrix, basically. Okay, so I'm not going to go into more detail, just have a look for yourself. Then what else do we have to do? So up to here we have, okay, we have the simulation running, and then we have the fact that we are going to use reinforcement learning with a QLearning algorithm. Okay, so what else? How do we put all that into code? Okay, because that's what you are wanting to do here. So very simple. Then for that, in OpenAI is very well organized to do this, because it allows us to separate the environments from the training algorithms. So what that means is that you can generate different environments, and well, you can have the same environment actually for a task, and change the algorithm, just the algorithm of learning, and then see which one is the one that is providing the best results in a very simple way, as you are going to see in a few minutes. But first thing that we need is to create the environment file. What is the environment file? Well, the environment file is the file that describes how to provide a reward, how to compute the reward for the task, and how to apply the actions to the robot, and how to get the new state, the observations, the new situation of the robot, and how to get all this information and pack it so that you can provide to the learning algorithm. And then the learning algorithm will learn based on that, the reward, the current state, and yeah, well, after you have applied an action. Exactly. Okay, so let's go and let's build the environment file. So in this case, for this task, I'm going to provide you with an already made environment. Next week, we are going to learn how to build your own environment for your own robot. And we are going to use a more complex robot, not that one, but a hopper robot, a robot that has to jump and has to maintain itself on the ground without falling down. Okay, so let's construct this environment file. And for that, first, what we are going to do is to create a configuration file with all the parameters that we are going to need. Then for that, let's go and where are we going to put the code of the training? So we are not going to use the simulation workspace, because the simulation workspace is only for simulations. And we already have the simulation done and running here. So the simulation is closed, let's say. Then for all the code that you would run into the real robot, so it's the code that you will run into the real robot, that doesn't matter if this code is executed in the simulation or in the real robot, then you have to go to the CADKIN workspace and put it there. So let's go to the CADKIN workspace here, and you will see that I have already created this here package for you that is called the Carpal V0 training, and contains some files here. Okay, so we'll go with those files in a few minutes. By now, let's go again with the environment, and let's create this Carpal QLearn params YAM. For this YAM file is going to contain the parameters that we are going to use in the training algorithm. Some of them are the ones that we have described here for the QLearning. Okay, let's go and create it. So come here to the Carpal V0 training, and then create a new directory, right-click, new folder, and call it config. Okay, so then inside there, create, right-click, new file, and call it Carpal QLearn params.yam. Please use the same names as indicated there, because otherwise some of the code that I have already provided will not work, because it's expecting some things, and etc. So just let's do that. Let's follow the name convention. Then let's open this Carpal YAM. It's empty, and copy these values here. You can just select everything, copy, and here paste. Okay, so what do we have here? Well, those are different environment variables that the algorithm is needing. So I will go into detail afterwards of these ones, environment variables. But what I want to show you first are those ones here. Let me increase the size so you can watch it better. Yeah, so oops, here. So those are the QLearn parameters. Those are parameters that are required here. Among them, there is the alpha, there is the gamma, and then there is the epsilon and epsilon discount. Those are additional parameters that are not described in this equation, and that, well, they are more specifics for implementations of the QLearning algorithm. So I'm not going to get into detail of that. But they are necessary for this reinforcement learning. And then we have the number of episodes and the number of steps. Those two parameters are the key of the training. So the episodes in reinforcement learning means the amount of times that we make the robot try to. So let's say, hey, please try to balance this. Try to balance this. And then we allow it to balance until the pole falls down. And then we say, okay, you fail because the pole fell down. But that's the number of episodes. By doing those trials and using this reinforcement learning algorithm, the robot is learning which actions allow to him to maintain the pole for longer times, because the reward will be higher. So the number of episodes is the number of trials. And then within each trial, how many steps, how many actions do we allow the robot to take? So we allow for 50 actions. And then we say, okay, let's try now. So you have 50 trials, 50 actions to try to maintain the pole there. And then many times the pole falls down before the 50 steps have been reached. So even that's too much sometimes, but it depends on the task, okay? But basically, those two concepts are very important, and we are going to see that in a few minutes. So let's continue with that. That's the config file. Then let's create a main launch file in order to launch the simulation and load the parameters into the param server. So by creating this main launch, when we launch this main launch, the whole system will boot up and will be ready for us to train, to start the training. So let's create that carpool training, new folder, call it launch. And inside the launch, create a new file called main.launch. And inside that file, copy this launch file. Basically, I'm not explaining that, but it's very simple. It's load the parameters that we just created here. Remember to save, okay? To save, press File, Save, or you can directly here do Control-S. It will save. And so save both files, loading the parameters and launching the simulation. That we have launched here the simulation manually, but then later we are going to use this launch file. That is easier. Okay, so now let's create the environment file. The environment file is the file, as I mentioned, that executes the actions on the robot, then computes the reward based on what happened because of the action. Then what happened? Oh, the pole fell down. Oh, the pole maintained without falling down. That's great. Then it computes the reward and then captures the current state, based on the sensors of the robot, what is the state of the robot, at which position of this line is the robot, and at which angle is the pole, at which velocity is moving each part. So that's what it captures, and then it provides all that information to the learning algorithm. So here, let me just create that file, carpool v0m.py. Here, go to scripts and create a new file and call it like that, carpool underscore b0 underscore env.py. And you open it and copy this code that is in this cell. Okay, this is the environment. It's a lot of code. Yes, I know. It's a lot of code. Yeah, so just select everything on the cell, copy, and then come here and paste. And remember to save, okay? Remember to save the file. Okay, so we have the environment. Let me go further and maybe, well, let me explain you a little bit of some functions that are important in this environment. Okay, so let me just go to the important ones. So, well, one of the important things is that we are registering this environment into the register table of available environments for OpenAI. This is a function that OpenAI is using for registering new environments that are not the ones that OpenAI has created. Because we have created this new one about the carpool, we are registering here using this function that is provided here by the gym. That the gym is the OpenAI gym libraries. Okay, so basically that's it. We'll go more detail next week on this, okay? But this is mandatory. Then you have to create this class that inherits from Gazebo environments. And here, basically, so you do on the initialization, you capture all the parameters from the param server. As you remember, the mean pole angle, max pole, max base velocity that we have included here. Mean pole angle, max base velocity. So here, so we are capturing those parameters because they are important for the environment. Okay, so let me go back to this configuration file because now those parameters are relevant. So as you can see in the configuration file, we have two kinds of parameters. First one are the environment variables parameters, and the second one is the learning algorithm parameters. So both of them can have an impact in how your robot is learning or not. So it depends a lot on those parameters that maybe your robot will not learn at all. Even if you are doing everything correctly, you are using the proper algorithm. But based on that, maybe it will never learn, or it will take forever, for ages to learn. Okay, so you have to play that. That is why we have decided to separate all this important information into a config file that you can change quickly and then relaunch your simulation, or spread into many, many machines. Like we have here, what we call the gene computers, where you can initialize many different computers with different simulations, different learning algorithms, or whatever. So configuration files. But this is not something that we are going to see today. So going back to the configuration parameters, what are those parameters about? Well, those mean pole angle and max pole angle are the angles that we allow the pole to, as maximum, to be turned before we consider that the robot has failed. So remember that the parameters are in radians, seconds, and meters. So these are radians that corresponds to 23 degrees. So if the pole is on one side or the other more than 23 degrees, then we consider is finished. So you failed. Go back and do another episode. Okay, so try again. And yeah, Heinz is indicating that he doesn't have the gene computer section. Yeah, because this is only allowed for the paying users. Okay, so the gene computers. So going back then, max base velocity, this is the maximum velocity that this is allowed to move. The maximum pose on X, and the minimum is the maximum position from the center on this rail that the robot can move in one direction or the other. Then the running step is the amount of time the control of movement will be executed during this step here. if I go to the reinforcement learning cycle, when we take an action, so in this case, the only actions that are allowed to this robot is move to one side or move to the other. And how much time do I have for this, for the robot to move to one side to another? So only 0.5, half a second. And then on each command, what we can do is to increment the position in one side or on the other. And this is the maximum amount of each command, basically. So as you can see, all this affects the environment because it affects how the action will affect the robot. Okay, so those are the parameters that we are getting here inside the environment. And then here in the environment, there are two important functions. One is the, let me see, what's the step is one, and the other one is the reset. Yeah, well, the init, yeah, step and reset. Yeah, so here the step. The step, well, first the reset. Yeah, the reset is the function that sets the whole system back again to the initial state once you have done one episode. So when you do an episode and you say, hey, please try to do it, and then it falls down, and you say, okay, you're done, stop. Then you say, okay, try it again. But before it tries again, we have to reset and put it back again to the stand position. So that is the reset function. That has to be well created because otherwise you cannot set the same starting condition for all the episodes. So that's the reset. And then the other one that's very important is the step. The step is this is the function that is executed after an action has been decided by the learning algorithm. If you remember here in the reinforcement learning, there is the agent that decides to take an action. Okay, so the one that decides to take an action is in this case, is the QLearning algorithm. So the QLearning algorithm is visiting his state matrix, this matrix here, and says, okay, in which state I am? So I'm in state 3. And then which one of those actions is the one that takes more probabilities of success? Then it decides, okay, let's decide this one. If everything is the same value, then let's decide this one, for example. Then it decides is the number 2, for example. Then this is action number 2. Then this step function is the one that receives the number 2 action, says, okay, number 2 action. What is the number 2 action? Okay, in this case, for this example, number 2 action doesn't exist because we only have 2 actions, number 0 and number 1. Move to the left or move to the right. So basically increase to the left or increase to the right. Then if here we receive 0 or 1, then we decide, okay, so if it is 0, then we decrease. If it is 1, we increase. And then we send that to the joints, to the joint, because it's only one joint, the joint here. And then we move it, the robot. We move it for the amount of time that we have configured here, the running step. And then afterwards, we make an observation. So what it does is called this function that checks what is happening. What is happening? What's happening? Did the pole fall down? At which position is the car pole, etc. And based on that, it generates a reward. If it didn't fall down, then it provides a 1. And if it did fall down, then it provides a minus 200. Basically, that's the environment. We'll learn more about that on the next class, okay? Next Tuesday. But we have it here, everything, with all the needed functions. So that I explained already, this, and then, so now let's make use of that and of the QLearning algorithm. For that, this is the main thing that I would like you to understand, is the start training algorithm. So let's create that on the scripts. Go to scripts and create a new file. Call it start underscore training dot py and open it. And let's copy the content of this cell here. You can select the cell, then press Ctrl-A to select everything, Ctrl-C to copy, and then come here back and press Ctrl-B. Or you can copy paste as normal, as you know. So save it. Remember to save it, okay? I'm going to explain you how this works. And here we have Stelianos that is asking a question. Wouldn't it be better to use a different reward than rewards you better when you are closer to the vertical? Yes, that's an option. That's an option. However, if I remember properly, so you can provide rewards that are based on the amount of angle that is close to the vertical. That's what Stelianos is suggesting, and that is correct. But if I remember correctly, with this example of the carpool, the interesting thing is that the robot can learn how to balance that with such simple reward. So that's super nice because it doesn't require that the person who is programming this knows about the problem. It just says, oh, you have done it correctly, you have done it incorrectly. That's all that I'm going to tell you, but not how. Okay, so that's a theory, and it works for simple examples like this one. In other cases, it's not like this. And then you have to do a kind of reward engineering, like you are suggesting. So yes, so that's a lot of discussion about that. Okay, let's go with the training retraining file. And what do we do here is basically we generate an instance of the environment that we have defined. So this is the Jim. Please create an instance of this one. That is the one that we have defined here in the cart poll environment. So we have registered it here like this. Okay, so create that, then generate the training results directory. So it's going, when we start this, it's going to generate a training results here directory where you can see the results. And then it gets the parameters for the QLearning algorithm, all the parameters here that we have set up here in the config file. Okay, then it creates an instance, initialize the QLearning algorithm. It says, hey, please create an instance of the QLearning with those parameters. And this action space, that is, the action space is N, is the number of actions that you can take on that space, and has been defined here in the carpool environment. And it's only 2, because it's only move to the left or move to the right. It's only 2. Okay, so in any case, it starts with the parameters, and then we have a QLearning algorithm that is running, and we have an environment that is running. So the only thing that we need to do is to put everything together. And what we do is two loops. One loop is for the number of episodes. Remember, the number of episodes is the number of trials that we allow the robot to try to maintain until it fails, or until it reaches 50 steps without falling down. So we do this, number of episodes, and inside every episode, we allow the robot to take action for 50 steps. This is the N steps parameter that we put into the configuration file here, 50. So we say, hey, yeah, you are on a new trial. Please start taking actions for 50. You can take up to 50. Okay, so take the first one now. Then what it does is go to the QLearning algorithm that it contains, this is the one that we have created here, then it contains this matrix that you can see here. Well, for the specific case, okay, this is for the case of the rooms here. So in our case will be something different, but you get the idea, okay? So, hey, take one action from this matrix. And because it's the first one, so everything is random, it will take some random action. But you don't have to care about that because this is already implemented by the QLearning algorithm. So it takes an action and provides this action. Then this action is provided here to the environment step function. So here is the action, and then this connects to this other file, the environment file that you remember, that is the step function here that receives the action and then does what I have mentioned here. Decide which one is, computes the velocity, and then publishes, moves the join based on that. And then provides the, what it does provides this, as I mentioned, is the observation. So is the current state, where is the pole, where is the car, and the reward, how good have you done. And also it provides some done. So in case that the pole has fallen down, then it says, hey, you are done, you have failed. So basically that's it. And with this information here, we provide this information to the QLearn algorithm here. And then the QLearn is going to learn. It's going to learn based on that, following the equation here that we have seen here for the QLearning. This one here. Okay, so basically that's implemented inside here, the learn. So this QLearning algorithm is going to learn based on that, and then just finish the loop and try it again. If it hasn't been done, if the pole hasn't fallen down, then it comes back here again. And then selects another action and moves the robot based on that action, gets a reward, makes the algorithm learn, and then repeats until all the steps have finished or the episodes have finished. Okay, so, and then the rest are logs for plotting, etc., many details. Okay, so that's it. The only thing that remains is that we put the QLearning algorithm on the file, and then we execute and see what happens. Okay, so here I have included a QLearning algorithm implementation made by Victor Mayoral, that it's a CTO of ROS Robotics. And he has created this implementation of the QLearning. I think it's quite good. And so just create here on the scripts, create a file, new file that is going to be called qlearn.py. And inside this file, copy this code and paste it. Then you can have a look at the algorithm and see how all the parameters follow the explanation of the algorithm, or how the algorithm has to work. Okay, so we have everything ready, I think. So the only thing that remains is to launch it and see if it starts training or not. So let's close here the simulation. So if you have the simulation still running, go to the shell where you open it and just close it. Control-C. It will take a while to execute, to shut down. And then what we are going to do is to launch the main launch that we have created here in the carpal training. Remember, this main launch is loading the configuration parameters and launching the simulation. So let's do it. Copy this command here. Basically, it's launch the main launch that we have created. So, and here, okay, very good. So we have an error here, as could not be else. Okay, yeah, okay. So there is an error here. It's my fault when I prepare the documentation. You have to come here and change here instead of training. No, that's correct. So let me see. File doesn't exist. Carpal, QLearn params. Okay, yeah. So I didn't put an S at the end here of the name. I don't know if that happened to you. Params. Oops. So here the name of the parameters should have an S at the end. Carpal QLearn params. Let's launch it again. And there it is. It should appear here. This message indicating waiting WebSocket should disappear and should appear again the simulation post and the robot with a pole facing up. So it's loading, and there it is. Okay, so we have the simulation there and with the parameters loaded. So I'm going to now launch this training algorithm. Let's go for it. And for that, we need another shell. So go to Tools and add another shell. And let's put it here beneath and copy this command. Basically, it's ROS run. Please execute the training algorithm, the training script that we just saw. It's the one that does all the loops of episodes and steps. So let me put it here like this. Then if you launch this algorithm, then the robot should start moving and the pole falling and computing the reward and indicating the different episodes, etc., etc. So it is supposed that if you leave that for a certain amount of episodes, then it will be able to run and to learn to maintain that. However, this is not going to happen. And this is your homework. So you have to find why it's not learning. Based on this code and all the information that I have provided to you, you must be able to find that. So figure out why it's not learning properly, even if you leave it for a long time. And then post it beneath there, beneath the comments of the video, of this video. So you put the reason why, and also way to, oh, you have to change here this or this parameter, or this code is wrong, or whatever you find. I don't know. Well, I know, but I cannot tell you. So then try to do that. And then for the person who posts this the first, then you will get a month free access to the Robot Ignite Academy. So you can learn a lot about ROS in that academy. That's our academy that we have online, and we have many courses related to learning about ROS. So basics, navigation, perception, manipulation, autonomous vehicles, more about OpenAI Gym and TF. Well, you see drones and many things. So if you post the solution there, the first one will get a month free access to that academy to learn everything about that. And in case that you don't want to participate on that, but you want to still use the academy, you have here a coupon for 7% discount, but it's valid until the next class, okay? Then finally, don't forget to attend to the ROS Developers Conference. That's an online conference that we are giving in the same sense as these live classes. We are giving on July ROS Developers Conference, where experts from the world, not from our team, but from the world, they are going to explain about the different subjects of ROS and how to apply this to your robot. So you can have a look here about some of the confirmed speakers and some others that are going to be confirmed around this week. And they are going to explain the same way as I'm explaining here. So you are going to get the material. You are going to get a follow at the same time as they are explaining and do the simulations. And actually, you are going to get also one specific book that we are compiling that is called the ROS Developers Guide. That's free for all the attendants. And basically, that's it. So let me know if you have any question. I will be here for some minutes more. And so that's it, basically. I see that today everybody was very quiet and there were no many questions. So I think it's good because there was a lot of people there, and I suppose that you were all trying to follow and understand. And here it's a question: can you speed up Gazebo to make the learning process faster? That's a very good question, and yes, you can do it, but it depends on how you do it. So the first thing is that your simulation, if you do less heavy your simulation, then it will run faster than real time if it's not heavy. Then if your simulation is very heavy because it's a very complex robot or something, there are many small tricks that you can do. Like, for example, you can change the step of the physics engine loop update. You can change that. It's a parameter in Gazebo. And by changing that, you can move it forward. But this depends on what you are trying to control inside your simulation, because you can reach situations where one object gets inside another. So this has to be taken with care. Okay, that's one trick. And other tricks is to, for example, all the parts that are on the system of the simulation that are not necessary to move, then you can make them static, so they will be easier. Another one is to use simple shapes for the simulations for the collision definition of the object in the simulation. So don't use the mesh to define the collision. Use the mesh only for visualization. Basically, that's it. I think that there are many other tricks there. I don't remember now. So I hope that this helps a lot. Mahid Hussein, he said, can you suggest any good book for beginners? For beginners about what? It's about reinforcement learning, or it's about ROS? What are you talking? If you could please specify. Atul says, any good book to start for industrial robots? Could you also provide the website address where QLearning was provided? You mean, okay, a couple of questions here. Any good book to start for industrial robots? So good to start with industrial robots. I presume that you mean to start with ROS Industrial. I presume that. About the industrial robots in general. Okay, so about ROS Industrial, then the best way that you can do is to go to ROS Industrial. And here there are some tutorials that you can do that are quite good. The tutorials are here. I don't remember exactly, but you can find it here. Another thing that you can do, of course, is to come to the Robot Ignite Academy and check our ROS Industrial, course that teaches you a lot about this, how to use MoveIt, how to create a URDF and do motion planning, etc. So it uses several different robots. That's about that. Then if you want to learn about the robotics for industrials, like kinematics and all that, then what I would suggest you is that you, let me see here. So let me see, you have here one that is called here Robot Academy, that contains many university open online robotics education courses. So you can learn here about industrial robots and kinematics, etc. And could you also provide the website address where QLearning was provided? So I presume that you mean that one. So the link is there on the notebook that I have provided to you. Then Mahid Hussein says it's about ROS, is about book for beginners. Yeah, of course. The best book, really, the best book for beginners, it's our books. I mean, it's bad that I say that to you, but because it's the truth. It goes for beginners. ROS Basics in 5 days. And then you get access to the different simulations that we use here. That's in the case that you don't want to use our academy. That the academy, you will learn very, very fast. So that, for me, that's the best book that you can see. And then Martin Shaw, he says, will it be a series of OpenAI tutorials with ROS, or is this a 2 video parts of the carpal example only? No. Yeah, so yes, there is a series of OpenAI tutorials that we are doing. So still, we haven't found the subject, decided about the subject for the last week. So next week in July is dedicated to learning with robots. So next week, we are going to work with a hopper robot. It's a super nice simulation of a robot with a single leg that has to maintain itself there and has to learn how to maintain there. So that's where we are going to see how to create an environment for a robot. Then on the next week, it will be about TensorFlow applied to robotics, how to recognize objects captured from the feet of the robot. And still not decided about the last week of June. If you have any suggestions, please tell us. Otherwise, we'll see how everything goes, the questions of the people, etc. So Atul says, thank you very much to you. And then thanks a lot, Ricardo. It was great class. Estilianos, thank you, Estilianos, very much. And Arnaud, he says, change some of the parameters of QLearning Parameters, after which episode you should see improvement. Any script to show convergence? Okay, yeah, maybe we are going to dedicate this because that's not an easy thing to tell you after which episode. So this is not, it's not straight. So there is no equation that can tell you after which based on the parameters or else. So maybe it's a good subject to do this about that, to talk about that on the last week of June. Yeah. So sorry, Arnaud, that I don't have the answer. Well, I cannot answer you that question. Okay, so you will have to wait a little bit. Any script to show convergence? I don't have it. I don't have it. Okay, so guys, thank you, Martin. Thank you very much for everyone for attending this class. And I hope you like it and you learned a lot. And if you have questions, please say that on the video, beneath the video. I will answer all of them. And please give us a thumbs up if you like it, and subscribe to the channel, press the bell, because we are publishing a new ROS video every day, a new ROS video showing how to do things. It's not about blah, 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 blah. It's about how you can do this in ROS. So that's super interesting and super practical for developers. That's for developers. Okay, thank you guys. Thank you all, and see you next week. Bye-bye.